thermomechanic analysis, hydraulic dams, concrete, loose materials, the structures and bridges, reinforced concrete, RC, steel, pre-stressed and post-stressed, RC, tendon stay, etc. Cable structures, non-residential buildings, industry plants, skyscrapers, sports stadiums, quality control, and procedures in construction works, forensic structural analysis, project redesign, checking, and validation. Now we'll proceed to show previous webinar summaries. Here we have a model in which we wish to perform a modal spectral analysis of a water tank. It shows the foundation, the supporting structure. In this view, we can see the crack formation and extent of a cover structure, which, if calculated by hand, closed form solution, we will not be able to visualize the crack locations and extent. Here we have a concrete slab bridge with a moving load, which is self-explanatory. Here we have a model of a nonlinear impact. You can think of this as the typical test of shooting a 2x4 at 100 miles an hour, representing impact on windows and doors, which is a standard test for wind-resistant products. Here we have a nonlinear lateral buckling. Buckling is a nonlinear solution which normally shows failure below the yield strength of the material. Bridge stakes construction. There are loads that, if not looked at in a simulation of the staging or erection of a structure, can cause failure at the site. Cable axis displacement, thanks to the powerful nonlinear capabilities of MARC, is a very simple thing for CivilFEM to model and analyze. Here we have a three-dimensional model of a moment steel connection analysis. Again, MARC has powerful capabilities to allow the nonlinear loading and unloading, showing plastic deformation after the loads have been removed. Here we have a source structure interaction CivilFEM model. Today's model would consist of two buildings, a building called office building, a circular shape, and a rectangular building with a overpass shown connecting the two buildings. This view graph shows that we would have a 5-story building with typical height of each story about 12 feet, Typical slab thickness is 6 inches, and the walls are 10 inches thick. The material will be concrete with ultimate compressive strength of 6,000 psi or 6 ksi. Also, the reinforcement steel have a yield strength of 60,000 psi or 60 ksi. The nomenclature of the beams and columns are black for beams, as you can see them around the circumference. This is a plan view. The green, which is part of the columns for the rectangular building to the right of the view, and the gray circle represent circular columns. The section size are, the beams are 24 inches deep and 14 inches in width. The rectangular columns are 24 by 24 inches, and the office building have a diameter 24 inches. The final product will look as shown in this image, and that's what we're going to pursue today. Now we are entering CivilFEM. Here we have the options that we're going to utilize are already highlighted. Three-dimensional modeling, static. It's going to be structural. And the options are 2D versus 3D, static versus transient, modal, harmonic, buckling, which could be a failure occurring below the yield strength of the material. This one is today's structural, and it could be seepage as water seepage to ground, and thermal analysis. It is advised usually to save the model every few minutes to ensure that if there's a failure of the computer called crash, that we could recuperate from the hard drive the model. Now we're going to save the model. Now we're showing the different options. Now Python is the scripting language that we're going to use. And we're going to demonstrate a pre-existing model for illustration purpose. Now we see the text at the right window, and this text can be created as we create a model, such as a typical floor, and then once we have it, we just create a loop around it in the text editor. We just simply run as any computer program or any macro, and we're going to see on the left corner the geometry being created. Now we have the points, columns, beams, and plates or slabs, and it's that simple. Very intuitive. Now we're going to start with the model step by step. This was only shown for illustration purpose only, to get an idea what to expect in this webinar. Now we're going to create a new model, and again the highlighting, we're going to save it. Now we're going to pick the system of units. We'll choose feet. We're going to use feet, and it's called the Imperial Units or U.S. Customary. You'll see on the left that we can mix the units, and CivilFEM will keep track and provide the proper conversions as necessary. We're going to work with two systems of coordinate system. One will be cylindrical for this building on the left, and one Cartesian for the one on the right. Now we're going to define the local coordinate system for each type of building. One circular, that will be cylindrical, and one rectangular or Cartesian. At the origin, we're going to create a on the right, we can see the coordinate systems created by the user. We're going to create another Cartesian coordinate system for the rectangular building. Now you can see on the right that shows the global, which is the basic CivilFEM. The cylindrical was the one user defined. And now we're going to create another Cartesian, which will be a local coordinate system, user defined. Now we have the new user defined coordinate systems. Now we're going to create 3 points in the cylindrical coordinate system for the circular building. That looks like these 3 points will be sufficient to create the entire model for the circular building. Now we place the cylindrical coordinate named already, and we're going to draw the first point, which is 12 points away from 0. At any point, the coordinates can be modified to locate the point at the proper location. Using references, we can create subsequent points from the first one. So the second point is called point 2. Is 24 feet to the left of our first point. And we say the reference with respect to the second, another 24 feet to the left of it. Now we have the basic 3 points that we stated will be created. Now, because we're going to copy in the clockwise direction, we require an axis of revolution about the parallel to the z-axis. And it'll be in the z direction. And it's what is known as a unit vector. Now we'll zoom in to show it. Now we're going to rotate 3 points in the clockwise direction. We select it. I'm going to rotate them at 30 degrees increment, 11 instances. That easy. Now, keep in mind that we are working at ground zero or the foundation level. So these points can be the bottom, the footer of the columns, and anything from there in the vertical direction will belong to the suspended slabs. The points drawn are shown here on the right, and they turn blue when selected. If you want to see the numbering, we just turn on the name. Now let's draw some points for the rectangular building. We're going to draw these 9 points, and then we're going to mirror them about the Before we draw these points, we must activate the user-defined Cartesian coordinate for the rectangular building. Because the points will be drawn from with respect to the origin of that user-defined coordinate system, not the global nor the cylindrical previously defined. If we make a mistake, we could easily erase the entities and recreate them. Now we completed the promise points at the upper symmetry for the rectangular building. Now we're going to select the points that we want to mirror about the x-axis of the local coordinate system for the rectangular building. But first we need to create the unit vectors for us to be able to copy and mirror. The first unit vector is a unit vector in the x direction, and we'll call it axis z. Now we can see the two vectors. Actually, sorry, all three vectors, x, y, and z. Now we can see the axes, cylindrical and rectangular. Also, we turn on to make it more obvious, more visible. Now we're ready to mirror those 6 points selected and shown in blue, and we're going to mirror them about the local x-axis. There you are. Now we're going to create the vertical lines representing columns to the first floor. We select these points and we translate them copy to the height of the building, which is 12 feet. 10 feet, I'm sorry. Now we're going to create a portal Now we have beams and column in the shape of portals by connecting the points directly, vertically, horizontally. The vertical lines are geometrical entities and not finite element entities. That would happen when we create them during the meshing phase of this webinar. Now we're going to rotate copy in the clockwise direction about the center in the z direction of the cylindrical coordinate system. It will be 30 degrees 11 times. But before we make the copy, we must select the entities to be rotated about the cylindrical coordinate system. Now we're going to draw the curved beams for the floor of the second floor, which will be the ceiling of the first floor, or ground floor. There's several options. We would choose to have 3 points around the circumference and its radius. The first 2 points belong to the segment for which you're going to create the area, and the third one defines the direction of the curvature with a given radius. Now we have the first curve. Second curve. Now the given radius, or radii, are with reference to the center of the cylindrical local coordinate system. Now we're going to copy curved beams, actually the curves themselves, about the circumference 30 degrees, 11 instances, and there we have it. And we will apply the same process to the rectangular building, and we could just observe the steps we're doing. First step will be to project copy in the vertical direction the full height of the rectangular building for 1 story. Now we're going to create portals in the X direction and the Y direction for subsequent copy. Now we're going to select the portals in the Y direction for copying its orthogonal direction, X direction. Now we're going to copy this in the X direction. Now we made the copies in the X direction. Now we have all the lines for the floor of the second story. Now we're going to create 3 lines connecting the circular building to the rectangular building. Now we're going to draw these walls of the circular building, and then the plates or suspended slabs. We're going to create another one here. We already created one. And for that wall, we need to create a curved line. To draw the walls, we're going to use polylines. We simply select the perimeter curves of each one. And the area of the wall is drawn automatically according to the selected curves. We can use the same procedure to draw the plates or suspended slabs. Now we have two plates of the circular building. Now we are ready to copy them in the clockwise direction using the local cylindrical coordinate system at the center of the circular building. There you are. At any time, we could color the components by groups and give it different level of transparency. For example, the walls can be made solid and the plates translucent. Now we're going to create the other plates. For the rectangular building, we're just going to choose to create two plates and then copy them in the positive y direction of the local rectangular or Cartesian coordinate system that we created. Our first floor is almost completed. We're going to copy 3 times or instances along the y-axis of our rectangular building. The rectangular beam plates, we could color them differently than the circular building. Now we're ready to define the material properties before we copy the walls and surfaces for the floors. To work with, for the selection of the material, we have here on the upper left-hand corner different types such as steel, concrete, post tension, rock, different kinds of rocks, metamorphic, types of rocks, different kinds of soils, and any property of general form described by possibly geotechnical data or other type of data available to the analyst. We see here the different codes. For this webinar, I'm going to use the ACI, American Concrete Institute, with a compressive strength of concrete of 60,000 psi or 6 ksi. For the sections, we have different options. We could take the sections from the built-in library. You can create sections by geometrical dimensions. One of the advantages that CivilFEM software has is that if you generate different sections in a project that you have already realized, and you initiate a new project, you could load these existing sections without having to recreate them. In this case, we're going to use simple rectangular and circular sections from the library. The beam sections, the material, we have to define it. When one create the material, you can see that you have options for cracking, for instance. As well as different level of curves. The curves representing different age of the concrete. Now we continue with the creation of the sections. For the beams and columns, they have the same cross-section information, but notice that the units can be mixed, inches and feet. The program will keep track of the necessary conversions for consistency of units. We created a section for the beams. Now we're going to create one for the columns. We have a rectangular column, 24 by 24, which is 2 feet by 2 feet. And now one circular or 24-inch diameter. When I create a section, we could view it. At this point, we only have a section without reinforcement. That would appear later. Now we could define the reinforcement. By defining the bar properties, the rebars, with the pertinent code ACI. And again, as we mentioned at the beginning, it's a 60 KSI yield strength of the reinforcement bars. Now we have the definition shown on the right hand side. When we pick them, if we pick the circular column on the right, the left shows the details. And it's ready to have the reinforcement added to this full definition. Now we see the box can be shown such that the CivilFEM can check the design if necessary. For now, we're just going to analyze. The program can actually select them in a design phase. This can be done for all types of elements: beams, columns, slab. Now that we have created all the properties and materials, we're ready to replicate the building in the vertical direction. We will create 5 stories by replicating the floor of the second floor in the vertical direction. We can see how quickly the 5 stories are being copied, created in the vertical direction. CivilFEM has the ability to allow the user to create groups of entities such as walls, columns, beams, slabs. This facility is useful for the viewing, pre-processing, loading, and for post-processing viewing of results. For instance, we're going, for illustration, create group of walls. This makes it easier for us to view by selection of groups the different kinds of entities. Such that if we want to see walls, we can just turn our group on. Once we select the groups, we can move them to a group named by function, be walls, slabs, etc. These groups can be found on the selection of groups. It can be selected quite readily. For example, we're going to take out of view and only the walls will be shown. In this case, we can mesh for the walls. They can have color, For illustration purpose, we only show 3 walls groups. Now I'm going to mesh. We're going to use the option mesh. Okay. The type of elements could be beam, truss, shell, solid cable, connections, and discrete masses, among other things. When the walls have shells, we're going to go ahead and mesh as such. This step is when we put the properties. The walls will be assumed to be 6 inches thick. I'm going to mesh just that one wall. Notice that steel can be located. Number of bars, separation, spacing in all the directions in the plane and the cutting vertical reinforcing. The mesh type can be either triangular or rectangular. The size can be specified on the left, and other parameters to control the refinement of the resulting mesh. Right now we have one structural group of elements. Now we can clone this mesh with its properties. For those walls that are the same, which in this case it is. Now we can mesh the entire set of walls shown. It's asking us to save the model prior to meshing. In case we have to revert, we simply go back to the copy. Now the mesh is being created. You see the mesh now, and the same procedure can be used for the other element types such as beams, columns, and plates. The models appear as shown. Once the mesh is done, following the same procedure as demonstrated in the meshing of the walls. In the next webinar, we're going to constrain the model and load it. And we're going to analyze and see the results. To complete this first webinar in the series of 3, we'd like to introduce our ability to have you consider the International Masters in Theoretical and Practical Application of Finite Element Method and CAA Simulation. The 23rd edition was began in February of 2017. The FAA Masters program is fully online with virtual classrooms, forums, video conferences, and e-learning, similar to how worldwide teams operate. CA Solution has partnered with UNED, Spain's largest online university, to offer you the chance to obtain an advanced degree in finite element method and CA solutions. The National Distance Education University unit is a leader in the implementation of cutting-edge technologies applied to distance learning with over 2,500 students worldwide. It is one of the largest universities in Europe. The program has the foundation, and the program can be either mechanical or construction branch. We have in the foundation these modules, same as application and practice. The software utilized in the training are well established and appreciated for its effectiveness through many decades in the actual industry of engineering. MSC's software, Magneto Schiller Corporation, has Patron and Nastran. ANSYS has mechanical, CFD, and Maxwell, which is electromagnetic. CivilFEM is powered by Mark, and CivilFEM for ANSYS is designed by Ingesiver. For the computation for dynamics, we have Metacom Technologies, and XFlow is for Next Limit. And we also have Model by Frontier. The registration fees will be described here for the first item, expert module, with a total cost of $2,700. It has $1,350 for enrollment fee and the balance for the training material. The rest you could read as shown. We are very appreciative for your participation in this webinar. You will be receiving your certificates via electronic email, and we again thank you for your participation. If you have any questions, you can contact us with the email that you have for us with questions and ideas how to improve the quality of future webinars and any ideas or what plans to present. Should you have any questions, again, you're welcome to help us out in making it more beneficial to all of us, and you're welcome to contact us. I hope that you'll be attending this next webinar and you'll describe your experience to your associates in your network.